We've come to know metabolism as the symphonically regulated network of cellular reactions. They can be of multiple types. Remember talking about catabolism, or the breakdown reactions, versus anabolism, or the buildup reactions. And then, of course, we talked about those amphibolic pathways, which are primarily catabolic pathways, but because they produce intermediates that can be used as building blocks in anabolism, called precursor metabolites, we call them amphibolic, or having a dual nature. Let's zoom in and look a little bit closer at a situation where we're degrading an energy source. Now, just for fun, let's say that this is a wonderful sprinkle donut. Now, I don't eat donuts, but I'm telling you, it's a great place to start, right? Because it's a high energy molecule, a carbohydrate, and that can be broken down or stripped and ripped of its high energy electrons, and it can be converted into smaller molecules. So if we start from a high energy molecule, we know that enzymes catalyze each one of the steps in a pathway, and that these breakdown reactions yield energy. And because these reactions are also oxidations, we know they yield high energy electrons. Now here I'm showing the breakdown, or the splitting, of one larger molecule into two smaller molecules. Now we know that all of these are intermediates, so we might say that this is intermediate A, intermediate B. And since we're starting with a fictional sprinkle donut, we're going to call this a fictional metabolic pathway, where these are all fictional intermediates. But understand this to be a catabolic pathway, a breakdown pathway, in which we're seeing the larger molecules breaking down into smaller molecules, and we're additionally seeing the generation of the products from that. And of course we know if you're breaking down a high energy molecule, you're getting energy out of it. So we reckon that this pathway is going to at least eventually net some ATP. Now, it might be that it nets that ATP much later in the process. Maybe when intermediate E is converted into intermediate F, there's some generation of ATP. So we know that one product coming out of a catabolic pathway, we would expect to see ATP. But additionally, we know that these molecules are getting repeatedly oxidized, stripped and ripped of their high energy electrons. So we additionally expect to see the generation of high energy electrons. We know they don't run around naked in a cell, so we expect to see the generation of some electron carrying molecules, some cofactors like NADH, or potentially FADH2. We know some other, and let's actually come over here and make a list of what we call the reducing power. Reducing power is the name that we broadly give to those molecules that carry around high energy electrons derived from the stripping and ripping of electrons off of a fuel molecule. So reducing power includes NADH, it includes FADH2, it includes NADPH, and let's talk about these molecules, each one very special. And when we write a metabolic or catabolic breakdown pathway, a lot of times we get lazy and we just show that NADH is evolved from the pathway. That's in fact how you would recognize a catabolic pathway, is a generation of reducing power and ATP. But we're being lazy in that, because in fact, if we were to look at the balanced reaction by which NAD+, so the molecule that is in its oxidized form before taking on the electrons, getting reduced by intermediate C when intermediate C is oxidized, because where there's an oxidation, there's a corresponding reduction. So we know that NAD+ is going to take on 2 electrons. And in a balanced reaction, we know those electrons would come bound to protons. And so our balanced reaction would be 2 electrons plus 2 protons would generate an NADH But notice this is an NAD+, so if it takes on one electron, it would just be NAD neutral. But then also, it would take on another electron. That one would have to come with a proton and make NADH. So what that means is that 2 electrons are taken onto this molecule when it's reduced, but only 1 proton. So to balance our reaction, with every generation of NADH, we're actually also popping off a proton. Now, those of you who get a little bit jazzed on exercise will recognize that every time that happens when you're breaking down a sprinkled donut, you're generating some protons, and that's why we sometimes talk about the burn of acid production when you're working out. So we've got these balanced reactions, and it's very important to recognize that there's a special name given to the 2 electrons plus 1 proton that is carried by NADH. We collectively call this a hydride anion because, of course, it's more negative than positive. So we say in a sexy-minded lingo that NAD+ carries a hydride anion when it is reduced. Now, the same is true for NADPH. You could write the same balanced reaction for NADP+. In fact, the molecule looks the same, except for that it has a phosphoryl group attached. So I'll leave you to write that balanced equation. However, when we look at FADH2, we might recognize that things are a little bit different. For one thing, when FAD is oxidized, it begins as just FAD. It then takes on 2 electrons plus 2 protons, but notice because it was uncharged at the get-go, it just becomes FADH2, and there is no generation of an excess proton because both electrons are taken on in the form of a hydrogen atom. So that's a little different balanced reaction. However, the thing that unites NADH and FADH2 is that ultimately the electrons that they carry go to the electron transport chain. So NADH, remember that it is a pizza delivery cofactor, aka it's a co-substrate rather than a prosthetic group. So NADH delivers, literally, physically delivers its electrons to the electron transport chain. And at the electron transport chain, it transfers its electrons from itself, who doesn't desire them as much as the next carrier in the electron transport chain. And throughout the electron transport chain, there are many electron transfers from molecules that desire the electrons less to molecules that desire them more. So let's actually talk about what some of those molecules are, and we can even, in fact, get a little bit nerdy about the standard reduction potentials of those components within the electron transport chain. Now, if we want to be really physically relevant here, we might say that this first pathway might be taking place in the cytosol of a cell, and then that the electron transport chain, remember, if this is a eukaryotic cell, is taking place within the mitochondrion. So the inner mitochondrial membrane is what I'm drawing right now, the cristae, remember the enhanced surface area, and we've got our ETC components that are spanning the inner mitochondrial membrane. And those are the components to which these electrons are getting delivered. Now, there's a lot of nuances in that, and we're going to talk more about those later, but ultimately electrons from NADH do get delivered to the first component of the electron transport chain. They get dropped off there. NADH goes back to being NAD+, and of course, true to its pizza delivery notoriety, it will go pick up more electrons. But that first component of the electron transport chain clearly desires the electrons more than NADH did. So let's take a look at the standard reduction potential table so that we can see what desires electrons more than NADH. Standard reduction potential is a term that relates the desire that a molecule has for electrons in a complete and entire electron transfer, that is within a redox reaction. Notice that if we look at something like NADH, it has a negative standard reduction potential. And so anything that's on the table below that, that is to say with a higher, less negative standard reduction potential, has a higher desire for electrons. So said another way, we could say that the molecules on the bottom of the table have the highest desire for electrons. So as we go down, we are seeing increasing desire. So in a complete electron transfer, the molecule that has the most desire for electrons is oxygen. Ah, maybe that triggers you to think something. Aerobic respiration? You got it. In aerobic respiration, that's another way to say that oxygen serves as the final member of the electron transferring relay team that we see within the mitochondrion of a eukaryotic cell or across the cytoplasmic membrane of a bacterial cell. So we could say that these electrons, as they get transferred through the ETC, through the electron transport chain, it's like as if this electron power was a currency of power that had to first go to a bank to get exchanged for the more recognizable currency, ATP. So let's go back to our drawing. And let's recognize that as NADH transfers its electrons to the members of the ETC, all with a higher desire, and eventually it transfers them onto an oxygen molecule in aerobic respiration. Water's given off, right? We know that from our exercise last time. And we recognize that the resulting energy release from that is used to pump protons into the inner membrane space. So there is a hydrogen ion gradient that accumulates across the inner mitochondrial membrane. Now we also know that that hydrogen ion gradient, it's extremely powerful, and you guessed it, it can be exchanged for ATP. So there's a beautiful machine called ATP synthase that also spans the inner membrane of the mitochondrion in a eukaryote. And when it allows hydrogen ions to swoosh back in to the mitochondrial matrix, it powers the production of ATP on the inside of the matrix. Awesome. You might also recognize that as being a process that you know the name of. It's called OX-phos. Possibly one of my very favorite terms in bar none. So we recognize then that this is what the electrons from the stripping and ripping of NADH off of the donut are used to do. Now, let's just take a moment to talk about the other player in all of this, because no matter how you look at it, whether ATP is made in a pathway, this is called substrate level phosphorylation because it's at the level of a substrate. Remember, there's an enzyme that catalyzes the reaction in which intermediate E is converted into intermediate F. So intermediate E is the substrate that's getting acted upon by the enzyme, and that enzyme is able to use that to make ATP. So the ATP is made so when ADP is phosphorylated, that ATP is made via something we call substrate level phosphorylation, different than OX-phos. And let's label OX-phos, oxidative phosphorylation. So let's take a moment to just look at a picture of ATP and talk about why it's special. Well, ATP, this is going to make everybody feel good, because ATP is actually special because of its mediocrity. That is one good-looking molecule, totally mediocre, and in that it is wonderful. So notice that ATP looks like exactly what you thought it was going to look like because it's adenosine triphosphate. So you're recognizing the ribose ring. It's not deoxy, right? Has a hydroxyl in position 2. So you've got the ribose ring, and then notice at position 1 you've got the adenine base. That's what makes it ATP and not something like GTP. If you put a guanine there, it would be GTP. And of course the TP means triphosphate, and that is where the special part of the molecule comes in, because there are some high energy bonds that occur in the triphosphate region. At the alpha phosphorus, we see a phosphoester bond, and notice that this is special because it has a delta G naught prime of hydrolysis of negative 14 kilojoules per mole. So let's make sure that we understand that when that bond is broken, it gives off 14 kilojoules per mole. Well, that's good, but it's not great, because as we take our attention away from the phosphoester, right, P double bond bond O, to the phosphoanhydride, which is P double bond O bond P double bond O, then we recognize some real power, approximately negative 30 kilojoules per mole. This is like more than double what is given off when the phosphoester linkage is broken. So this can power some real action. We can recognize, in fact, that when ATP is hydrolyzed or broken down into ADP plus PI, that yields quite a lot of energy, negative 30 kilojoules per mole. That energy can be used to power other reactions, and that's where we'll focus our attention today in class. So that energy that can be given off there. But likewise, we know that if we reverse this reaction, so if we look at this as being a reversible reaction, that if ATP is made, then energy must be put in. Now, hey, pretty cool connection coming about here, because if we go back to our image, we can recall that ATP could be made in two different ways. It could either be made via substrate level phosphorylation, where the energy to make the ATP came from intermediate E, from a molecule. So there's the energy coming from that molecule, a high energy molecule, or the energy could come from the proton motive force. So recall from the electron transport chain and from the pent up proton gradient and ox-phos, right? The energy was coming from the PMF. So the root of the energy to make ATP is what differs when we're talking the difference between substrate level phosphorylation and oxidative phosphorylation. Now that is radtastic, and it is going to let us get started with our active learning for today.